Now, the question there says this. The question there says, you're looking at the matrix. That's the matrix which is in the question there, like this. It's no longer the matrix which operates with numbers. It's just like a matrix which operates with symbols this time. But still, that's the matrix. It's the augmented. It might be an augmented matrix of some, the augmented matrix of some system. Sorry, right? The question there says, it is given to us. It is given to us that the matrix, the system associated with this matrix has infinitely many solutions. That's what's said in the question. Given this information, we have to figure out what kind of relations on A, B, C, and D we should have in order to meet this. In order to produce this information, that we have infinitely many solutions. So the idea of the question, we have to convert this matrix to the row echelon form. This time, it no longer will be the arithmetic conversion. It will be something which operates with the algebraic expressions with A, B, C, and D. And we have to see when we will come up with the row echelon form, we have to see what we should do with the A, B, C, and D to make this matrix have at least one non-leading column on the left-hand side and no leading columns on the right-hand side. That's the principle. That's the sort of idea what we're going to do now. So if I do my row echelon form, the first step, of course, is vanishing these two elements. To vanish these two elements, I need these two elementary row transformations, like this. I have to take the second row and subtract the first one multiple with A. Third one multiple with A. It's relatively easy arithmetic. Let's just do it here. Well, good. So the first row stays as it was. Now the last one, first element obviously is 0. That was our objective. For this element, it will be rather lengthy expression because if you multiply this with A and you subtract from this one, it will be 1 take A squared. That's the one. If you do the arithmetic here, it will be A take A squared. Right? You multiply this A with another A and subtract from this A. That's the one. Right-hand side is just like this. Something similar happens to the third row. Again, first element is 0 on the third row. It was our objective to vanish that element. That's why we have 0. Here we have A take A squared. And here we have 1 take A squared. Right-hand side still looks like this. And that's how the matrix with the first. That's how my matrix will look after the first two set of transformations. After the first set of transformations, elementary row transformations. Now, let me ask you this. What do you think we should do with this matrix now? Like, we already created one pivot. This one is already the pivot. Now we have to create a pivot here. Do you think 1 take A squared will go for a pivot? So if you want to vanish this element, the kind of row transformation we need, elementary row transformation, here, is, do I see it? Here, that's the one which we need, right? We need to take the third row and subtract. Well, we have to multiply this row with the fraction like A take A squared over 1 take A squared. But because they have a common factor, right? We have to multiply this row with something like this. A take A squared, 1 take A squared. That's the kind of factor we need to convert this coefficient into this element into this element. Everybody agrees with that? But in this fraction you have like a common factor, right? 1 take A in the numerator and 1 take A in the denominator. That's why my coefficient here become a little bit simpler, like this. Now, if I do this transformation with this matrix, it will be some arithmetic involved because I'll show you. Okay, I'll show you. So I put all of the arithmetic on the slide. So the first row stays as it is. The second row stays as it is. We don't no longer change the second row. Changes will happen to the last row only now. If I do my changes to the last row, look what happens. 0 here, 0 here. That was our objective, to make it 0. For these two elements, they will be rather lengthy if I do all of the manipulations with the involved symbols. That's why I just call them X and Y. I just call them X and Y, and actual expression for this X and Y, I'll show it down here. Look at this. For X, what we do? For X, we take this element, here it is, and we subtract this element scaled by this factor or by this factor. I right? Yes. Well, yeah, that's the one. We took this element and we subtract this one scaled by this factor. If you do all of the manipulations you have, or you have to do, yeah, it's a common factor here, in fact. And if you further simplify this last expression, this last one, because here you have difference of squares, right? You can put it like 1 plus a take a, which is 1, and 1 plus a, which is something like this. That's the expression for x. Now for the y, again, I'm sure you can figure out the details. If I do the arithmetic here, if I just bring something together, what's happening here? Well, this bracket, if you bring it to the common denominator, it will be 1 plus a, so it will be looking like this. And the final expression for y, which I'm happy with, is this one. Done. All of the routine stuff is done. We have my row echelon form, don't we? That's a row echelon form, pivot, and pivot. And we can now address the question when my matrix, when the associated system has infinitely many solutions. Am I right? No. I said pivot, and I said pivot. No. I told you should say no. Pivot must be non-zero, guys. 1 take a square, who said it's a non-zero? In general, it's not a pivot. We didn't test for that. In fact, it will be pivot if I have extra assumption. Do I have this extra assumption? Yes. If I have extra assumption that the y not equal plus minus 1. Only in that case, in fact, it was actually obvious even here when I did my division here. You can only do this step when under the such conditions. In which case, this will be row echelon form. This will be row echelon form, and this kind of system, the system which is also associated with this row echelon form, will have multiple solutions when x and y equal 0. Now, x and y equals 0, look what it means. X equals 0, it means that this fraction equals 0, but the first bracket cannot be 0 under this assumption. So the only possibility is the last bracket being 0. So x equals 0 converts into a equal negative 1, 2. Oh, a, sorry. And y being 0 converts into this whole. So it means, like, if I alter it a little bit, d equal 1/2 c take d take sorry. No. d plus 1/2 d take c plus b equals 0, which we can solve. You can solve here, well, that's the condition which we have. You can actually alter this condition a little bit. You can alter this condition a little bit, but still it will be, that will be the case when your system have infinitely many solutions under this extra thing. What should we do with this extra thing? Well, what should we do now with the other a's, when a equal 1 or a equal negative 1? What should we do with that? We have to consider this case separately. We don't have to substitute in the original matrix, in fact. We can sub in already in this case, because step from here down here doesn't require this extra assumption, but this step does. So we have to sub this value into this matrix, and then see if we can take it to the row echelon form. And I did it here, look at this. I did it here. The a equal 1 case, that's kind of matrix you will be looking at. If a equal 1, all of these bits, they will vanish. And that's how the right-hand side will look. And a equal negative 1 case, that's the kind of matrix we will look at then when a equal negative 1, right? If I sub in here a and negative 1, 0 here, negative 2 here, 0 here, negative 2 here. And this one, in fact, it's already row echelon form. That's my pivot. So if I want this matrix to have infinitely many solutions, I must ensure that there is no pivots on the right-hand side. So I have to vanish these components. So the condition here will be C equal B equal D, which will make infinitely many solutions with this extra A, with A like this. And the condition here, of course, I have to do, this is not row echelon form yet. I have to swap these two last rows. If I swap them, the matrix will look like this. Now it becomes a row echelon form with 3 leading columns on the left-hand side. So in this case, we don't have any room for multiple solutions. So this case must be discarded. So the final answer will be this system we started with will have multiple solutions under such A and such conditions on B, C, and D, or under such A and such conditions on B, C, and D. Any